So let's now discuss some of the examples to make the concept of microstates and macrostates clear. We'll take up some ordinary examples to understand the technique of counting the number of microstates, and thereafter finally we'll come to some physical examples as well. Okay, so let's consider the most common probability experiment, tossing an unbiased coin. You know, an unbiased coin means a coin which has got equal probability to give a head and a tail. Okay, so you know that the outcome of tossing an unbiased coin will be either to get a head, right? The outcomes are getting a head or getting a tail. So getting a head is one of the accessible microstate of the coin, and getting a tail is another accessible microstate. So there are two accessible microstates. So I can say the number of microstates in this particular experiment, or for the system here is an unbiased coin. So the unbiased coin can manifest itself in two of the states, either the head turning up or the tail turning up. So each of this state is a distinct state, and we call them as microstate. Okay, number of microstate is equal to just what? 2, right? And both of these microstates are equally probable, right? So I can say that the probability of each of this microstate is what? The same, because the microstate head can occur. See, the chance is 1, and microstate tail occurring here is also what? 1, right? So we will say that each of these microstate is what? Equally probable. Now let's go to the tossing of two unbiased coins simultaneously. Tossing of two unbiased coins simultaneously. So let's say what are the possible outcomes. So we'll just take. So I'm dividing the outcomes like this. What are the possibilities? Both head can turn up. Both head can turn up. Then one head, one tail. It can be the outcome, or it can be both tail. So there are 3 possible outcomes. So each of these outcomes I can call as a macrostate. Each of these outcomes I am calling it as a macrostate. Macrostate. Okay, right? Now what are the different ways in which these macrostates can occur? Let's say, for example, both head. In what ways it can occur? You can see the number of ways, or what are the distributions I can call. See, this is the distribution. Okay, what are the possible ways in which this macrostate can be achieved? Both head means first one has turned head, second one has also turned head. So there is only one way in which this particular macrostate can be achieved. Head I am writing. Now one head and one tail, in what all ways it can happen? So either it can happen like this: the first coin has shown head, the second coin has shown tail. That is one possibility. Is it all? No. You know what can also happen? The first coin has shown tail, and the second coin has shown head. So there are 2 possibilities corresponding to this particular macrostate. Okay, now both tail, you know, there is only one possibility, only one possible arrangement corresponding to the macrostate, both tail. What is that? Like the first one, it is tail. Both the coins are turning out tail. Now see, the third one, what I'm doing, I'm taking the number of. So this symbol shows the number of. Okay, number of microstates. Number of microstates. So I told you 1, 2, 3. Okay, so each of this particular 1, 2, 3, what I have numbered as 1, 2, 3 represents a macro state of the system. If you want, you can just call this one as a macro state of the system, because here we have got two particles or two coins. So two coins, both the coins mixed together, we can call it as a macro state. So mixer condition is known as, bulk condition is known as macro state. Both head is a description of the entire system, right? Now how that can happen, that shows the distribution. So this is what is known as a microstate. Okay, so how many number of microstate corresponding to both head? I can say the only one microstate is there. Similar is the case, or the same is the case with the third macrostate as well, which is the both tail. So tail, there is only one number of microstate. One arrangement only is possible. I told you each distinct arrangement is regarded as a microstate, right? So head, tail, head. So our macrostate definition was one head, one tail. The order was not mentioned. So this is a bulk description without specifying the details. So it can turn up that head, tail is one microstate, and tail, head also is another possibility, another microstate. So how many number of microstates are there in this case? So there are what? 2 microstates. You please note that the number of microstates, number of accessible microstate for different macrostates is not equal in this particular experiment. You can see that the second macrostate is having largest number of what? Microstates. It's a very simple system, because that is why the difference is only 1. Okay, other 2 are having 1, but this is having 2 microstates. When the system is large enough, having large number of coins, say that there are 1000 number of coins, okay, so then there will be a large number of distributions. Won't it be? Like even if it is 3 coins, you know, see this table will be becoming bigger and bigger, right? So there are number of possibilities there. Head, is not tail, then head, tail, head. Okay, no, it's not 2 head and 1 tail. So 2 tails and 1 head. There are so many possibilities like that. Okay, so then finally we have to think how all, in what all ways all these states can be attained. So you have to count the number of microstates, and you will see that there are actually a number of equations for all these things. The counting is not so difficult. So there are some permutation equations and combination equations which can be used on. Okay, so that you will learn in your postgraduate courses. Now I want to just give you an idea about what is meant by microstates and what are the basic assumptions of statistical mechanics. Okay, now, so these two are the tossing of coins or tossing of dice. You know, the dice what you are using to play your what do you say, snake and ladder, right? Okay, that cubical see what do you say, dotted wooden or plastic thing. So you have got now 1, okay, somewhere 2, 3, 4, like, you know, see, this is what we mean by dice, you know. Okay, we are using it in Ludo or whatever it is. Okay, now throwing of dice or tossing of an unbiased coin is just some physical activity, but you know, in physics we are basically interested in studying the behavior of physical systems like electrons. Okay, I told you statistical mechanics is usually concerned with the study of large systems involving electrons or photons, okay, etc. So in order to have a realistic experience of our physical systems, let me take up the third example. So what I have, suppose that my system is consisting of 2 spin half particles kept in a magnetic field. I'm making it very clear. 2 spin half particles kept in a magnetic field. You know what is my spin half particles? You have learned about the property known as spin. Spin means spin magnetic moment. Okay, modern physics will be giving you better ideas, and quantum mechanics will improve your ideas when you go to the concept of spin. You will learn that spin is an intrinsic property for elementary particles. Just like particles have got charge, particles have got mass. Some particles are having particular property what is known as spin, and they differ. Even if all other physical properties are the same, 2 particles can be different if they differ in another property what we are naming it as what? Spin. And spin is basically spin magnetic moment. Okay, and the spin of the particle, you can just see there are several reasons due to which the spin can arise. It can arise due to the orbital motion, or can arise due to other reasons also, because it's angular momentum. Okay, magnetic moment related to that. And see, let me denote the magnetic moment by EM. Magnetic moment by EM. So suppose I have two spin half particles kept in a magnetic field. If the spin of the particle is half, there are two possible orientation for the particles in a given magnetic field. Okay, there are two possible orientation for a spin half particle in a magnetic field. Okay, the relations is actually, it's given by 2s plus 1, where s is the spin. So 2 into, in the case of spin half particle, you will see that it's 2 into half, that is 1 plus 1, that is equal to 2 orientations. You have learned all these things, okay, in many other languages, using many other terms. I don't want to give you more details at this point of time, because you are yet to learn about the ideas like spin in detail in your modern physics. I am not aware up to what you have learned. So anyway, let me give you one thing. I can take your idea. You know about magnets. Okay, magnetic dipole. Anyway, is not, you have learned about electric dipole or magnetic dipole. So for example, you consider that there is a magnetic field. Somewhere there is a magnetic field B, vector B, we represent, right? B or H, whatever it is. Okay, and you keep a magnetic dipole here. Magnetic dipole means a very small magnetic needle. Okay, so having north pole and south pole, right, say, and suppose that the theta be the angle that is made by the magnetic dipole. Every magnet having north and south pole is actually known as a magnetic dipole, right? Tiny magnets, and each atom behaves like a tiny magnet, and so each atom is having a magnetic moment, right? Electron is having a magnetic moment. So we are learned about Bohr magneton and all. I don't know, okay, whether you remember it, leave it anyway. So each atom can be regarded as a tiny magnet. That's a basic idea. So let this be a magnet. So a magnet is a magnetic dipole, and magnetic dipole is characterized by a property known as magnetic moment, usually represented by vector M or vector mu. So both of these symbols are used. M was the symbol that you used in your +2 classes in magnetism. So you know that whenever you have a magnetic dipole kept in a uniform magnetic field B making an angle theta, then this magnetic dipole do possess something what is known as potential energy, magnetic potential energy, represented by U, and you derived that U is equal to minus m dot B. Hope you remember this one, this equation, or it is equal to minus mb cos theta, minus mb cos theta. Okay, you learned this one while learning about torque and on a magnetic dipole and potential energy of a magnetic dipole, or at least you remember in the case of its electrical counterpart is easy to remember. Okay, what is that? The potential energy, electrical potential energy of an electric dipole kept in an electric field is what is known as U is equal to minus, instead of M, it will be P. It's not electric dipole moment, P dot E minus P dot E. And P cross E was giving you the torque. Okay, torque was given by P cross E, right? And the potential energy is given by P dot E. So instead of P, you use EM. P is the dipole moment, M is the magnetic dipole moment, otherwise known as simply magnetic moment, okay, which is a property of the magnetic systems. And this magnetic moment of the given bar magnet that you measured in your tan A, tan B positions in deflection magnetometer experiment. Okay, it denotes the strength of the magnetic property, right? So anyway, two spin half particles are kept in a magnetic field. So the question is that if you have a magnetic field like this, in what all ways this magnet can align itself in equilibrium? You know that either the magnetic field or the magnet can align itself parallel with the magnetic field. So the magnetic moment vector can be parallel to the magnetic field. That is what is known as stable equilibrium position. Theta is equal to 0. Theta equal to 0 is known as stable equilibrium position. Or there is yet another possibility. The magnetic field is like this itself in a particular direction, but the magnetic moment of the given atom or the particle is in the opposite direction. This is also an equilibrium. Both of these are equilibrium. So this corresponds to theta is equal to 180 degree, where theta is the angle between these two in the first diagram here. This is theta. So the magnetic moment. So like this is north and this is south, and here I'm writing this is north and this is south. So that's meaning. So this is known as parallel alignment, and this is known as anti-parallel alignment. Okay, so why it is theta equal to 0 is the stable equilibrium. This is not a stable equilibrium because you know when theta equal to 0, as per this particular equation, magnetic moment, potential energy will be equal to minus mb. Cos 0 is equal to 1. So minus mb. So here u is equal to minus mb you get. And here when theta equal to 180 degree, you will get cos 180 equal to minus 1. So in this case, the potential energy of the system will be equal to plus mb. And you compare which energy is more. Of course, minus mb is more than plus mb. Right? In both the cases, the torque will be equal to 0. Torque equal to 0 in both the cases. Because tau equal to m cross b. Okay, and theta 0 equal to theta 0 or theta 180, you know, see sine 0 is 0 and sine 180 is also 0. In both the cases, torque equal to 0. So when torque equal to 0, we will say that the system is in what? Equilibrium. Rotational equilibrium. Okay, but there is energy difference. So we'll say both are equilibrium, but one is known as stable equilibrium, which corresponds to minimum energy. Minus mb is less than plus mb. Right? So we'll say that the first one is a stable equilibrium and the second one is a unstable equilibrium. Right? So there are two alignments. This is what I want to conclude. There will be two alignments possible for a spin half particle when it is kept in an external magnetic field. This discussion will be helping you to understand better what you are learning in your modern physics. In your modern physics, what you will be doing when you study about what is known as what you call Zeeman Effect or whatever it is, instead of drawing the external magnetic field like this, horizontal, usually in modern physics textbooks, this magnetic field will be drawn like this, vertically, usually along z-axis, and this vertical direction is taken not as y-axis, but it is usually taken as z-axis. Okay, and usually in textbooks you will see such diagrams. See the alignment of magnetic moments, spin magnetic moments like this, one alignment like this, and its components are just marked like this. Okay, and it's the components are shown along along this reference axis and all. What are the components and all? It is shown like this. Okay, so especially when you study about many particle, many electron systems and its coupling of the momenta, LS coupling, JJ coupling and all. When you learn it, you will see that, and you will see that there is a reference direction here, and this reference direction is nothing but the conventional direction along which an external magnetic field B is applied. Okay, and this particular magnetic field is actually shown along the horizontal direction in our these two diagrams. So just remember this one. So these systems are where only there are two possibilities for the stable arrangement, for the equilibrium arrangement, is what is known as two-level systems in statistical mechanics. So such systems are known as two-level systems in physics or statistical mechanics, because there are only two states possible, either aligned parallel or aligned anti-parallel. So now let me say that what are the possible microstates for a two-level system such as spin half particle. So I'm doing it it will be very similar to the tossing of two unbiased coins, you can understand. So let me write it. First one. What are first one? Okay, first macro state I'm writing. See, I will write the macro state is I can say that it is first macro state where the things are both the spins will say up, 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 up. Just try to understand what's meaning this up, up. You used to denote when you studied the electronic configuration and you used to write like this, right? Is it not? And we say that up spin and down spin. And what is this up spin and down spin? It only represents what the alignment of the magnetic moment with a reference magnetic field. As I told you here, now we are taking Z as the reference direction and we apply a magnetic field along Z direction. So if the magnetic moment is aligned with this one, we'll say that it's up arrangement. And if the magnetic moment is aligned in the opposite direction, we'll say that that is down alignment. Okay, and that is the there is a history behind the naming of up spin and down spin. There is nothing like that an electron is pointing up or down, or it is rotating clockwise or anti-clockwise. There is nothing physical related. Okay, it's all with reference to the alignment of the alignment of the magnetic moment of particular particle or an atom with a reference direction, which is usually applied along Z direction, which we regard as up. Okay, so if both the magnetic moment. So this one is what we call as up. This alignment is known as up, and this alignment which is opposite to the magnetic moment is known as what? Down. So there are only two alignments possible. So what can happen? I have two particles. So both the particles can align with the magnetic field. So this is particle number 1 and this is particle number 2, and the vector shows the magnetic moment of particle number. So there is m1 and this is m2. Both are equal. Please remember, identical particles. For example, 2 electrons or 2 protons. Let us take only charged particles, okay, in the case. So m1 and m2 both are aligned, so both are up spin. So when it is up, then what will be the total energy? You know, when it is aligned parallel, the energy will be minus mb. Energy for each particle will be minus mb. So there are two particles, so minus mb plus minus mb. So what will be the total energy of the system? It will be minus 2 mb. Minus 2 mb. So I can say minus 2 mb is the total energy of the system in the magnetic field, right? Let me say. Now the second possibility. What is the second possibility? One can be up spin and other can be down spin. Okay, up down. So what is up down meaning? Up down meaning one of the particles, say one electron, is aligned parallel to the external magnetic field. Okay, whereas the second electron's magnetic moment is aligned anti-parallel to the given external magnetic field. So this is known as up down. Okay, so one is aligned with its magnetic moment parallel to the external field, and the other particle is aligned with its magnetic field vector, magnetic moment vector opposite to the applied magnetic field. So we'll say that configuration is up down. So what will be the total energy? When it is parallel up, it will be minus mb, and when it is anti-parallel, it will be what? Plus mb. So what is the total energy of the system? The total energy of the system will be equal to 0. Now there is one more possibility here. What is that? It can be up down, means first particle up, second particle down. There is another possibility. What is that? Down up is not another possibility, another arrangement, because we have two particles. We consider these two particles are distinguishable. That is one thing very important. We consider these particles to be distinguishable now. Okay, now in this case also, okay, down up, this case also the total energy will be equal to 0. Now the third one is both down. So down down. What is down down? What is the total energy? Means both the particles are aligned anti-parallel with its magnetic moment anti-parallel to the applied magnetic field. So the total energy will be plus 2 mb or 2 mu b, right? So I can say that this particular one is a macrostate. This particular one is another macrostate. So there are altogether 3 macrostates. Okay, how do I classify the macrostate? I am classifying the macrostate based on their total energy of the system. So there is one macrostate with the total energy equal to minus 2 mb, another macrostate with the total energy is equal to 0, and another macrostate with the total energy is equal to plus 2 mb. Now how many microstates? Actually there are 4 microstates. Okay, 4 microstates are there. This is one microstate, this one is another microstate, this is another microstate, and this is another microstate. Is clear to you? Because each of these are distinct arrangements of the particles of the system. So there are 4 microstates, but 3 different macrostates I have identified. Okay, and so my question, which macrostate is having largest number of microstates? So I can say the second macrostate is having 2 microstates. Both other the remaining 2 macrostates are having only 1 microstate. So I will say that the basic assumption, there are some basic assumptions for statistical mechanics. One of the basic assumption for statistical mechanics is that all microstates, please listen to my words with care. Okay, micro and macro, with my pronunciation, it should not make any confusion. See that what I mean is that all microstates corresponding to a given macrostate. First one I say micro. All microstates corresponding to a given macrostate are equally probable. All microstates or each microstate corresponding to a given macro state are equally probable. That is one of the basic assumptions, fundamental assumption of statistical mechanics. Okay, and what does it mean? It just means that if our coin is unbiased, tossing the coin, it should be producing head and tail which are equal, so not with the equal probability. That's only meaning in the physical sense. So here you can see for in the third example, for I can say first macro state, there is only one microstate, so there is no any competition. Third macro state also, there is only one microstate, there is no competition. But for the second macro state, you can see there are two competing microstates. Okay, so suppose somebody asks which of this microstate is more probable. Will it be up down or down up? The answer, or the basic belief in statistical mechanics, is that both these microstates has got the same total energy 0. Okay, means they both of them belong to the same macro state. So those microstates, I mean these two microstates, okay, those microstates which belong to the same macro state, means having same total energy in my example. Okay, total energy was the criterion for classifying this one as a single macro state. So both these microstates will be having equal probability, and that particular principle or that particular assumption, which is very fundamental to the development of statistical mechanics, is known as equal a priori probability statement. Equal a priori statement. The statement of equal a priori probabilities. Equal a priori probabilities. A priori means prior to. Okay, so before we begin, that's meaning. Means before tossing the coin, we believe that the probability of getting a head is equal to the probability of getting a tail. That we believe before tossing the coin, and based on that belief only, that we are going to agree upon the result of the toss, right? And that principle is what is known as what? The statement of equal a priori probabilities. It states that each microstate corresponding to a given macro state are equally probable. Okay, and we will see more examples of physical systems in the coming videos. So try to read and contemplate on the topics what I have discussed. I just want to give you some physical idea which will help you to attend some entrance examinations also after your degree. So it may not be exactly in tune with your textbook, but so I have the aim of just giving you some practical knowledge also, which will help you to attend other things which are practically important, because our university syllabus does not always tally with the syllabus or question pattern of those central university entrance examinations and all. I just do this one by just analyzing those questions what has appeared. Okay, if you want to answer those questions in those examinations, better that we have a practical idea of what we are stating in the statistical mechanics module. Okay, so let's just discuss more in the next video. Thank you. That's for today.